there's a very special type of density curve called the normal distribution. Ooh, it's very special. It's very unique. And it's called normal distribution for a couple of reasons. Actually, originally it's really, if you want to talk all sophisticated and sound like you're really smart, it's called a Gaussian curve. Named after, you guessed it, Carl Gauss. I know you all know who he is and what he looks like. Or maybe not. Anyways, the Gaussian curve, or the normal distribution, it's called a normal distribution in large part because there are so many things that happen in nature that when you measure them, they all seem to follow this same kind of distribution. All right, and I've drawn it before, and I'll draw it again, but it's a mound-shaped curve that goes on infinitely in each direction at the end. It does not end. It goes down here and goes infinitely close. It's got an asymptotic relationship, so it's an asymptote. So it goes all the way down and keeps getting closer and closer to the axis, but never actually gets to it. The total area underneath it, because it is a density curve, the total area underneath it is 1, or 100%. The normal curve is centered at the mean, and 1, 2, I write the 3 standard deviations. Every time we do a normal curve, we're going to do that. And by every time, I really mean every time we do a normal curve, we're going to label the mean, and then you're going to mark off 3 equal increments that go out to almost all the data, and then 3 out to almost all the data. And there's a reason why we do that. Okay, and here's the reason why. The normal distribution, or things that happen that seem to follow a normal distribution, they follow a rule called the 68, 95, 99 rule. All right, so we're going to shrink that and put that over there, called the 68, 95, 99.7 rule. All right, it has a more sophisticated name, which I may have already said once before, called the empirical rule. All right, the empirical rule says that within 1 standard deviation of the mean, so here's the mean, within 1 means between these 2. Within 1, so could be 1 below, could be 1 above, but within that range, so I'll put a little line up and a line up. Within that range is 68%, or about 68% of the data. So if there were 10,000 measurements for the diameter of a tree in some plot of land, 68% of those tree diameters are going to likely fall in that range. All right, because tree diameters will likely follow a normal distribution. If you take an SAT test and they tell you what the average is and the standard deviation is, if you go the average plus 1 standard deviation, the average minus 1 standard deviation, and find those 2 values, about 68% of the students who took the test will be within that range of values. All right, and then if I continue going on, say, okay, well, within, let's go to here, how much is in that range? Well, you know it's going to be over 68 because 68 is the narrow part, but within that range is 95%. Okay, so that's a grand total width of 4 standard deviations. 1, 2, 3, 4 standard deviations. All right, and within 4 standard deviations, or sorry, the middle 4 standard deviations, within 2 of the mean, 95% of the data happens there. And then lastly, the very outside, which is out here, within 3 standard deviations, is 99.7. So virtually all of the data in a normal curve will happen within 3 standard deviations of the mean. All right. We will begin talking about, well, what makes something an outlier? Well, it depends on the scenario. Sometimes something that's out here or out here will be considered an outlier. So that would be, now remember, this is the outside of the 95%. So this out here on the left end, that's 2.5%. Because there's 95% total, 5% is left, 2.5% at either end. So a grand total of the 2.5 2.5, and the 95 gives you the 100%. All right, so if you're in the top 2.5% or the bottom 2.5%, you may be considered in some cases to be an outlier. It depends on the case and the scenario and the problem and the circumstances as to what is actually going to be an outlier. And that is a little bit in part of where the 1.5 IQR comes from with box plots, sort of. Not explicitly, but it's close. Close enough for us anyways. So that's the normal curve. Now, if I have a normal curve for test scores, so here I draw my normal curve for test scores, and this is a shorthand way of writing normal curve centered at 100 and a standard deviation of 10. All right, so while I didn't write it in there, this is mu and this is sigma. So if we happen to know that I have a normal curve of scores centered at 100, because that's the average, and my standard deviation is 10, so I go 1, 2, 3, and that's 3 standard deviations. So it's 3 10s, so it's 130 up there. And then 1, 2, 3 below, and mark that off as 70. If I have this as my normal curve, we already did this once, but if we find z-scores, x minus mu, that's a minus, divided by sigma. If I do that for every data point in this distribution, so if I take so again, let's say there's 1,000 people who took this test. Each person has a point somewhere in there. There's all these points, all 1,000 points that are in there somewhere. Let's suppose I take that point right there. All right, that point right there looks to me to be about, what is that, 92. Let's say it's 92. So this point right there is 92. All right, and if I find its z-score, I would do 92 minus 100 divided by 10. So that's going to be negative 8 divided by 10, or negative 0.8. All right. If I were to take every single data point in here, all 1,000 of them, and run every single point through this formula and get a z-score, I would have then 1,000 z-scores. And that distribution would be z, because they're no longer x. We centered at 0, and my standard deviations would be 3. Or, sorry, would be 1. So it would be negative 3 and positive 3 for my endpoints. So any number that was an actual 70 would have a z-score of negative 3. A score that had an actual score of 130 would have a z-score of positive 3. Why is this important? That's a good question. It's because this distribution is what's called the standard normal curve. All right, it's standard because if I take any distribution that's normal, doesn't matter what it is, if I know the mean and standard deviation, I take this entire distribution, if I run every point through this formula, I will get the z distribution. No matter what the average standard deviation was of the original distribution, when I run it through that formula, the standardization formula, I will get the standard normal curve. Which means I can simplify my life and know that no matter what I do, if I run a normal distribution through the standardization formula, it will give me the standard normal curve. If I take this other teeny tiny little curve, a normal curve, centered at 1 with a standard deviation of a half, so this up here, 3/2, that'd be 2.5, negative 1/2. If I were to take every data point in this distribution, put it through that formula, it would also give me that exact same standard normal curve. So really what I have is, I have a way to address or work problems or do stuff, basically, on a normal curve by first converting it to a z-score, and then we'll use a table of values and we'll figure out what that is, and then from that going and back into context. All right, so there's some examples in your book that are really good examples that I'm not going to read for you. Let's see, in the book we're using now, that's section 2.2, on normal distributions. There's some examples on page 116 and 117. Now, if I happen to be in a new book when you're reading this, then obviously it's going to be on a different page likely. But take a look at those examples, and we'll go through some in class on how to solve problems using the standard normal curve. All right. I do not have a question for you to answer in your reflection response. So what I want you to put in there is just one single word. That one single word will be the one word of the character trait about you that you think is best about you. All right, so the character trait about yourself that you think is best about yourself, but only one word only, please. See you in class.